And we're going to be talking about solving absolute value equations and absolute value inequalities. So this is a new type of equation for us to solve, and so we want to consider how we're going to go about solving this. Now, everywhere in algebra we solve equations in a very similar way. We try to get whatever it is by itself, and then we undo it. And this basic idea is going to help us as we start to move forward with other types of equations throughout this course, is if we can identify that we have some sort of quadratic equation. We get the quadratic part by itself, and then we undo it. When we have an absolute value equation, we're going to get the absolute value part by itself, and then we're going to undo it. And the new part you'll learn for each type of equation that we ever deal with is the whole how do we undo it thing. How do you undo an absolute value? And so we'll get to that in a minute. But that's kind of the idea, and we're going to kind of explore then what we're going to do and how we're going to do it and why we're going to do it. So we have an absolute value equation sitting in front of us. So we got to remember what it means to be an absolute value. That an absolute value means your distance away from zero on the number line. So the equation we're looking at, the absolute value of x equals 3, is trying to say if I have a number line and here's 0 on it, I want to find all the numbers that are 3 units away from 0. And so common sense or logic says you could step to the right 3 units, and that would get you a value that's 3 units away from 0. Or we could step to the left 3 units. 1, 2, 3 units, and that would also give us a value that's 3 units away from 0. So what value could x possibly be? Well, x could be 3, or x could be negative 3. Now this isn't exactly how we're going to solve each of these, but I just want to point that out, that is kind of what's going on here. That this basic definition is saying, I want to make sure that my distance from 0 on the number line is 3. Our equations are going to get more complicated, but they're all going to follow the same basic idea that we can probably usually have two answers, and we're going to get two answers because of the fact that we could either go to the right or go to the left. Now, we're going to see there's going to be weird cases where we're not going to get a positive and a negative answer, but oftentimes that's the case. Now, we can also visually see why this is going to happen if we think about this graphically. So if we think about this graphically, we could think about it graphically by saying y equals the absolute value of x and y equals 3 are two separate equations. And where those two equations touch at is where absolute value of x and 3 would be equal to each other. So we could actually graph each of those and see where do they meet at. And so y equals the absolute value of x. Well, that looks like a V. And it's going to go something like this. So that's y equals absolute value of x. Y equals 3 is a horizontal line. And if we want to say where do they cross at? They cross at, look at that, an x value of negative 3 and at an x value of 3. So we can actually think about it graphically as well to see why is it that we're getting these two answers. So we can either think about it through the definition of the absolute value, that is the distance from 0 on the number line, or we can look at it graphically to say where does the graph of y equals the left side match up with or meet y equals the right side. So based on what we just saw with the example of the absolute value of x equals 3, we're going to come up with what is called the absolute value property. And this is the rule that's going to teach us how to solve absolute value equations. Now it is really important anytime that we have a property in math, and so if you're reading through a textbook, this is where you're going to see a shaded box. Anywhere in math where you're learning a new property, you always want to look for this word if. You always have to know, when does this rule apply? Now, to bring this into light with something that you're probably very familiar with, if you think about the Pythagorean theorem as an example, the Pythagorean theorem only works for right triangles. And so you can't do the whole a squared plus b squared equals c squared if you don't have a right triangle. And that's part of the whole theorem, is to say if you have a right triangle, then a squared plus b squared equals c squared. Now technically that's actually a two-way street. It's actually an if and only if, meaning if you have a squared plus b squared equals c squared, then it must be a right triangle. But that's besides the point. What I'm trying to point out here is that you always want to look for when does a rule apply. This isn't just for every absolute value problem. This particular rule says if we have absolute value of x equals a, where a is a non-negative number. I'm going to pause there for a second because there's a few things going on. Now, one thing you'll notice going on is that I use a capital X there. All right, Brad, you have a shift key in your keyboard. Way to go. Now, I use a capital X for a reason. That oftentimes in math, when you see a capital X, it means this could be an expression. This doesn't have to just be absolute value of x. Maybe it's absolute value of 2x plus 7 or something like that. That we have to have an absolute value of something with an x in it, and that's equal to a, where a is non-negative. And so the other detail I want to point out here is that there's a difference between non-negative and positive. The difference is whether or not 0 is allowed. So when we say non-negative, that just means that a can't be a negative number, which means a could either be positive or it could be 0. So 0 is okay in this situation. So if we have this situation, then's the other big part you want to look for in any of these properties, is say, okay, so if this requirement's met, what does that tell me? Well, if we have an absolute value of x equals a, where a is a non-negative number, then either x is going to equal a or x is going to equal negative a. And that's what we saw with our example of absolute value of x equals 3. He said, all right, well, either I could take a step to the right and I'm going to be 3, or I can take a step to the left and I'm negative 3. And that's what this property says. It says either you can take a step to the right and you're a, or you can take a step to the left and you're negative a. And those are the only two possibilities that are going to happen. We can either go to the right or the left, and that's it. So now to put this in kind of simpler or more plain English terms, the two qualities that have to be met in order to use the absolute value property is that we need an absolute value by itself on one side, that's the whole absolute value of x thing, and the other side has to be a non-negative number. These are really important that we're going to check for these every single problem that we do that's an absolute value equation, is we want to see are these two qualities met. If they're not met, we cannot use the absolute value property. Instead, we're going to apply common sense, and we're going to see when that comes up. But we're going to try to use this property whenever possible when we're solving an absolute value equation. Look at our first example. As we look at this example, absolute value 6 plus 2x equals 4, we want to ask ourselves those two questions. Do we have an absolute value by itself on one side? And yeah, our left-hand side is just an absolute value. Yes, it has stuff on the inside, but what we care about is the absolute value of something by itself on the left side. Is the right side a non-negative number? Well, yes, 4 is a non-negative number. So because the two requirements are met, we can jump right into the absolute value property, which tells us the stuff that was inside the absolute value is either going to be equal to 4, or the stuff inside the absolute value is going to equal negative 4. So we could only do this because those two requirements were met. And now we've undone the absolute value. There's no more absolute value in my problem here. So now I can solve this just like normal. I can subtract 6 from both sides. I can divide by 2. There's one of my answers. I can subtract 6 from both sides. I can divide by 2. And there's my other answer. So I'm getting two answers here of -1 and -5, and those are my two answers to this problem. And just like any other problem, you can plug these back in, double check that they work, and I would advise doing that. You should always check your work. If you make a mistake, you may as well catch it before you report it. So plug them in, make sure they actually do equal 4 after you take the absolute value, and you're going to be good. So let's take a small step up in difficulty for example 2. We're looking at absolute value of x plus 1, equals 13. We're going to ask ourselves the two questions. Do we have an absolute value by itself on one side? And the answer is no. So we can't use the absolute value property yet. But could we modify this so that we can? Well, absolutely. And that's what we're going to do. And so we're going to subtract 1 from both sides, giving us absolute value of x equals 12. Please note that the absolute value is still there. We haven't got rid of the absolute value yet. We have to go one step at a time. We didn't have what was necessary to use the absolute value property at first, so we did something legal. We did a modification to it. Now we're going to start over. We're going to ask ourselves again, do we have an absolute value by itself on one side? Yes. Is the other side a non-negative number? Yes. So can we use the absolute value property? Yes. Because we can use the absolute value property, now we can go ahead and say the stuff inside the absolute value is either equal to the positive stuff or the negative stuff. And there's our answer to this example. Time for example 3. Time to step it up one more notch here. Do we have an absolute value by itself on one side? No. All right. So can we easily get there? Sure. We're going to go ahead and subtract the 8 from both sides. Now, once we've done a modification, we start fresh. We go back to the drawing board, back to the beginning, back to both questions. Do I have an absolute value by itself on one side? Yes. Is the other side a non-negative number? No. So because my two requirements are not met, I cannot use the absolute value property. So we're not going to break this up. So we can't break this up into two separate equations. It's not going to work. That's not a method that we can use to solve this problem. You might want to write that down. I'm going to repeat that. Because the absolute value property wasn't met, the requirements weren't met, we cannot break this up into two separate equations. We can't just remove the absolute value bars. So we have to use a different strategy for solving this equation. And the strategy that I'm going to suggest is what I call the common sense approach or the logic approach. And what we're going to do instead of trying to solve this by breaking it up into two separate equations is I'm going to look at the left-hand side and I'm going to say, I don't care what x is. I'm taking the absolute value of something. Once I take the absolute value, it's going to basically be a positive number. Now, yes, to be technical, it's non-negative because I could get 0 and I take the absolute value. But for the sake of this particular problem, that's not going to matter. Let's just call it a positive number. So that left-hand side is going to end up being a positive number because I took the absolute value of something. The right-hand side is -7. It's a negative number. And these two things are supposed to be equal. When will a positive number equal a negative number? Never. A positive number will never equal a negative number. Therefore, we have no solution to this equation. This equation will never be true. And that's all we've got to write then is no solution. All right, let's take a look at example 4. We have absolute values involved, and so once again, we got to ask those two questions. Do I have an absolute value by itself on one side? Well, sure. That's an absolute value by itself. That's an absolute value by itself on one side. Is the other side a non-negative number? Well, yeah. Once I take the absolute value, no matter what that x is, once I take the absolute value, that will be non-negative. So what we have here technically does fit those two requirements. And so that tells me I'm allowed to use the absolute value property to say the stuff inside the absolute value could equal the stuff on the right, so 6x plus 4, or the stuff inside the absolute value could equal the opposite of the stuff on the right. So now we have our two equations to solve. We have a little more work than some of our previous examples, but the big thing is the absolute value is gone. Now I do want to take a step back to say I sort of should have been a little more precise here. This will get you the two answers that work. Technically, what should have happened is we should have said 9x plus 1 equals the absolute value of 6x plus 4, or 9x plus 1 equals the opposite of the absolute value of 6x plus 4. Then we could use the absolute value property again. That's going to get us a total of 4 equations. They're all going to boil down to the same two equations we have written down there. So we're not going to worry too much about being super picky there, but if this was a more advanced math class, I'd go through all those nitty-gritty details with you. Just believe me, they're going to boil down to these two situations here. And then we just solve them. So for the equation on the left, we're going to subtract 6x from both sides. Then we can subtract the 1. Then we can divide by the 3, and there's an answer. X is 1. For the right-hand side here, we're going to want to distribute the negative. Then we can add 6x to the other side, getting us 15x. Then we can subtract 1 to the other side. We're going to get negative 5/15, which simplifies down to negative 1/3. And so we're going to get two answers again. Took a little more work to get there. But the big thing I want to point out is if you have an absolute value on the left and an absolute value on the right, then that really does meet the requirements that we were looking for. We do have an absolute value by itself on one side, and the other side is a non-negative number. I want to show you one last example of an absolute value equation before we get into the absolute value inequalities. And that's just because something kind of weird happens with this particular one. So if we start off with our same two questions, do we have an absolute value by itself on one side? Yeah. Is the other side non-negative? Yeah, because it's an absolute value. So we can use the absolute value property. And so we'd go with x plus 9 equals x minus 6, or x plus 9 equals the opposite of x minus 6. Great. So now we're going to try to solve these equations. Now for the one on the left, we try to get rid of this x on the right by subtracting x from both sides. In doing so, we're left with only 9 on the left and negative 6 on the right. Does 9 equal negative 6? No, it doesn't, no matter what x is. If this were our only part of the problem, we would say no solution. Now this doesn't mean there's no solution. We still have that guy on the right to work with. But that equation didn't lead us to a solution. Let's solve the one on the right. So let's distribute the negative. Now if I add the x to both sides, I get 2x plus 9 equals 6. Then subtract the 9. Then divide by the 2. I get this answer, x equals negative 3/2. Now as we report this answer, we're not going to report no solution and negative 3/2. That doesn't make sense. That's like saying, hey, what are your favorite colors? And for you to say blue and I have no favorite color. No, if your favorite color is blue, then just say my favorite color is blue. And same thing here. We're not going to say there are no solutions and here's one solution. That doesn't make any sense at all. We're just going to say we only get one answer this time, and that answer is negative 3/2. Now let's try to make some sense on why this happens. Now to make sense of why this happens, let's actually come back to our previous example of example 4. We got to see what graphically happens. If we go way, way back to example 1, when we first looked at these, graphically, we saw that we normally get two solutions because we were looking at where a horizontal line meets up with a v, with an absolute value. So going back to example 4, what was happening here is we had a v whose slope was 9, so we had a really steep v, and we had another v whose slope was 6, so it was a less steep v. They crossed in 2 places. So that's why we're getting 2 answers to example 4. For the example that we're working on right now, they both have a slope of 1 to them. So what's happening on this case is we have a v here and a v here that's parallel. So this line and this line are never going to cross, just as this line and this line are never going to cross. But where do our 2 v's cross at? In one spot. So they do cross in one spot, but where normally we'd be getting a second crossing, we don't get one because of the fact that they're parallel. And so that's what you can kind of look for to tell when this kind of weird thing's going to happen, when you can expect it, is when you notice that the coefficient in front of your x's are both the same. That's when you can say, oh wait, I remember seeing that from the video. That's normal, that's expected that I only get one answer here. All right, now we're going to shift gears to talk about absolute value inequalities. So we're going to be looking at inequalities that have an absolute value in them. So absolute values with a less than, with a greater than, with a less than or equal to, with a greater than or equal to. So that's what we're talking about right here. Now, as we move through the rest of this course, we're going to see lots of different types of inequalities. We're dealing with the absolute value inequalities right now. We're going to deal with inequalities in 2 variables the next lesson. We deal with systems of linear inequalities in 2 variables. We're going to deal with polynomial inequalities, rational inequalities. We deal with inequalities in a lot of areas. And what we want to try to do is we want to try to say, instead of coming up with a new strategy each time that we see an inequality, let's try to come up with one strategy that always works. And it's going to be very similar to what we did with the compound inequalities earlier on with the ands and the ors. So we have 3 steps listed out right here on the screen. I'll walk through them, but then we're going to try to break them down into even simpler terms. So the first step is that we're going to say, scrap the whole inequality. Scrap the less than, scrap the greater than. Let's just pretend like it's an equation. And the idea of this is to say, if we figure out where an inequality would actually be equal, that should theoretically be where it changes from being less than something to being greater than something. So it's going to be where we're going to change from being true to being false. It's going to be our border. That's why we want to pretend like something's an equation first, or an equality, is to say, let's figure out the border points between what works and what doesn't. And that's what the equation points are going to be, is the border. So then we're going to plot those solutions from step 1 and any other critical values. And you'll notice that I have critical values crossed off here. And the reason for that is the problems that we're going to deal with right now don't have what I'm going to consider critical values. And when we get to the point that we need them, I'll explain what they are. During this step, when we plot those solutions, we're going to pay attention to whether our original problem did allow for equality or not. So was it less than or equal to, or was it just less than? Because if equality was allowed in the original problem, and we found the point where we are equal, then we want to include that point in our final answer. So we're going to use things like a closed circle as opposed to an open circle. That if equality was not allowed in the original problem, then the point that makes it equal, we want to say, hey, this point isn't really included, so let's use an open circle. So that's why we're going to pay attention to whether the original allows for equality or not. Then in step 3, now we can have a couple different strategies that work for step 3, but in general, once we have our number line or whatever it is broken up by these points of equality, we can test points in each of the chunks, in each of the regions, to figure out whether that chunk or that region should be shaded or not. So we can test points and say, hey, does this make the original true, or does it make the original false? And so that's what we're going to shade. So to put these in simpler terms that are easier to memorize, step 1, pretend like it's an equation. Step 2, plot those solutions. Step 3, figure out what gets shaded. And so that's what we're going to talk about too in this lesson, is how to figure out what gets shaded. There's one method that will always work, but there's some tricks that might make things a little bit easier for us. So let's talk about one of those tricks. One of those tricks is if we have an absolute value situation, an absolute value inequality, let's graph what's going on as a v. And let's see why this works. So let's scroll off that page for a second. And let's suppose that we're trying to solve the inequality absolute value of x plus 4 is less than 6. So what I want to do is I want to graph y equals the absolute value of x plus 4 and y equals 6 on the same set of axes. So let me go ahead and use color to help us differentiate between these. Let's go ahead and look at y equals the absolute value of x plus 4, which means let's do a v that's shifted to the left 4 units. So that's going to look something like this. I'm going all the way to the top just so we can kind of see what's going on in this problem. And so this guy, once we connect the dots, looks like a v. Now the other one, the y equals 6, that was the right-hand side, that's a horizontal line. So I'm doing a squiggly line just so that it shows up a little bit better there. So those are the two. Now if we look at where they intersect at, that's kind of like our step 1. They intersect at x equals negative 10 and at x equals 2. Those are the values that would make it equal. Well, let's look at what happens as you walk left to right, though. As we walk left to right, notice that before the first intersection, the v was above that horizontal line. At the intersection, it changed to being below. Then as we got back to the next intersection over here at 2, we started to go above the horizontal line. Well, that's kind of interesting. Coming back up to the inequality want to know, hey, this v that I graphed, this absolute value, when is that under or below and y equals 6 was our horizontal line. So this question was really asking, when is the v under or below the horizontal line? And so if we come back over here to the picture, the v was under right there. So it was, let me go ahead and get this color over here. It was above here, then it was equal, then it was below, then it was above. So if I only want to know when it was below from negative 10 till 2. And that's actually the answer to this problem, is the interval from negative 10 to 2. Now this was a graphical interpretation of why this works. In the next example, we'll look at both a graphical interpretation and a little more of an algebraic way of going about it. But you want to keep this in the back of your mind. We're not always going to graph in this way, but this kind of gets you an idea of why it works so easily. So let's go through our 3-step process for example 6. Step 1, pretend like this is an equation. So step 1 says, ignore that inequality sign and just get absolute value 5x minus 3 equals 18. And I want to pause right here to show how important it is to be good at solving absolute value equations. That was the first half of this lesson, was solving absolute value equations. That's the first step then in all of these absolute value inequalities as well. So if you want to think about this from a student perspective of being just a good student, you're going to say, hey, this lesson here is 1/3 of my exam. I need absolute value equations for all of it. So this is basically 1/3 of what I need to know for this upcoming exam. Pretty darn important. So we've got to make sure we know that topic. So, absolute value equation. Do I have an absolute value by itself on one side? Yes. Is the other side a non-negative number? Yes. So I can use the absolute value property, which says either the stuff equals 18 or the stuff equals negative 18. And then I solve each of these. So I add the 3 to the other side, I divide by the 5, and I do the same thing over here. I add the 3, divide by the 5, and I get these two answers. That was the end of step 1. Step 2 is to plot those two answers. So I'm going to use a number line, and I'm going to plot negative 3 and 21/5. So far, I haven't actually plotted them. I've only labeled them. To plot them, we want to use either an open circle or a closed circle. And this is where we got to pay attention to the original inequality sign. Our original inequality sign had an or equals to in it, which means we want the points that make it equal to 18 in my answer. These are the 2 points that make it equal to 18. We want to make sure to include those in our answer, so we're going to use closed circles there. Now, that's the end of step 2. Step 3 was figure out what gets shaded. And I want to talk about 2 different ways to figure out what gets shaded in this problem. The first way is to use the whole idea of the V. Now, some people have a hard time with this, so I do want to talk about a second approach that we can take to this. The idea of the V is to draw a V that intersects our line at those 2 points. And this is really just our scrap work. Then we want to say, all right, what's happening on the left? On the left, the V is, let me go ahead and use a different color real quick. On the left, the V is above the line. In the middle, between my 2 numbers, the V is below the line. And on the right-hand side, the V is above the line. So if I go back to the original problem wanted to know when is the absolute value, or the V, greater than means above. Greater than is above, less than is below. And 18 is just my horizontal line. So that's my number line in this case. So I want to know when is the V above the horizontal line? Well, in a couple places, actually. It's above over there. It's above over there. So in terms of interval notation, that tells me from negative infinity to negative 3, as well as 21/5 up to infinity. And that's the answer to this problem. So that's kind of our graphical, easy way of getting the answer, is just to draw a V and say, when's the V above or below, and then figure out in the original problem, did I want to know when was it above, or did I want to know when is it below? Now, the other thing we could do to figure out where it gets shaded is, let me go ahead and start over with my 2 important numbers. This way is a little bit more of an algebraic brute force way. Let me go ahead and copy down the original problem again. The other way we could approach this is just by literally picking points to say, on the left, either all those points work or they don't. So over here on the left, let's test some number. So let me actually, just to make this clear, let me again kind of do my dotted line here. And if I want to test some number that's to the left of negative 3, I might test negative 4. And I would just plug that negative 4 into the original problem. And I just want to know whether this is true or false. So I plug it in, I figure out the absolute value of negative 23 is bigger than 18. The absolute value of 23 is 23. So is 23 bigger than 18? Yes, that's a true statement. So because that's a true statement, the entire interval must be shaded, because going back to what we saw in the picture before is that if we have the V, these points where we're equal are where we're going to change from being less than to greater than, or vice versa. Now for the middle interval, we need to test some number that's between negative 3 and 21/5. 0 would be a nice easy one to test because that just gives us 0 minus 3, which gets us 3 is bigger than 18. 3 is not bigger than 18. That's a false statement, so we don't shade that interval. Now 21/5 is what, 4.2? So if we're going to test a point to the right, we need to test something bigger than 4.2, like 5. So that's going to give us 25 minus 3 is bigger than 18. This gives us 22 is bigger than 18. That's a true statement, and so we should shade that. So this method, as you can see, works. It gets us the right answer. It's a lot more work, though. Drawing the V allows you to visually see what's going on and very quickly get to an answer. As we look at example 7, hopefully something jumps out at us here. Hopefully this minus 7 after the absolute value jumps out at us. So before we even pretend like this is an equation or anything, let's go ahead and do something completely legal. Let's go ahead and just add the 7 to both sides. Because it's perfectly legal, we can basically treat this handwritten thing now, treat that as our original problem. So this is our original problem now, and we're going to go through the 3-step process. Step 1, pretend like this is an equation. So if I pretend like it's an equation, it becomes equals 4. Once I've done that, and please write this step out, because one of the things I see often is people jumping right to breaking this up into 2 separate equations, and we can't do that. We can't do that until we go through all the steps. We have an equation now. Now we can ask, do I have an absolute value by itself? Yes. Is the other side a non-negative? Yes. So now I can break it up into 2 separate equations because I can now use the absolute value property. We're going to subtract 2 from both sides, subtract 2 from both sides, and get our 2 values. We now plot those 2 values on the number line. So we have -6 and 2. We're going to pay attention to the original inequality sign. This time we did not allow equality, so now we're going to use an open circle. Because we don't want to say these values here are part of our answer, because these are the values that make it equal to 4. And we don't want to allow equal 4. So now we're going to draw our V to figure out what gets shaded. So we draw our V, again, so that it goes through at the points where we're equal. And now if we look at what's going on, we're above on the left. The V is below in the middle, and the V is above the line on the right. I don't know why I used a lowercase e there. That was silly. Now we go back to the problem. The problem with the star by it, want to know when is the V less than means below the horizontal line. Where is it below? It's below in the middle. So now that I have it shaded, I can give an interval notation answer of -6 to 2 with parentheses because we're not allowing those endpoints. Now, we can find these values by plugging in a point from the left, a point from the middle, and a point from the right as well. But this is so much quicker. All right, we're at example 8 now. Now, example 8, we actually have 2 separate problems that we're going to look at, and we're actually going to look at both of them from 2 different perspectives. The one that I call the common sense approach, and the other with using the 3 steps. So I just want to make sure we're clear so we can kind of see the difference in what's going on. But we'll get the same answer no matter how we approach it. So as we look at this problem here, hopefully this jumps out as something weird in that we have a negative on the other side. And so if this were an equation, if this were absolute value of x plus 2 equals -3, then we'd say the answer is no solution. But I don't want you to jump right to that conclusion. We'll see why. That's actually not the answer to this. The answer to this problem is not no solution. So let me start with the common sense approach to this problem, and then we'll get into the three-step. The common sense approach to this problem is going to be, like we did with the equations, to replace the absolute value with the word positive, and replace the negative number with the word negative, and then just simply ask ourselves, when are positive numbers bigger than negative numbers? Well, that's pretty easy. If 0 is here and positive numbers are over here and negative numbers are over here, positive numbers are always bigger than negative numbers. Always. So if it's always, what values of x make this true? Any value of x makes this true. So our answer to this problem is actually all real numbers. It's the interval from negative infinity to infinity that would make this original inequality true, because it's always true. Positive numbers are always bigger than negative numbers. That's the common sense approach. Now, if we went with the three-step approach, let me go ahead and rewrite the problem real quick. Step 1 would be pretend like this is an equation. Step 2, well, actually, step 2 is plot them, so let me actually finish step 1. Step 1 is to solve it as though it's an equation. Well, absolute value equals a negative. When does a positive equal a negative? That's never. But we can't stop there. If we're going to do the three-step process, we better do all 3 steps of the three-step process. Step 2 is plot those solutions. Okay, sweet. I plotted them. I plotted nothing. But then step 3, figure out what gets shaded. We can figure out what gets shaded by either plugging a number in from the interval and seeing if it works or not, or by drawing the V. Now keep in mind that we have no border points that we plotted. Therefore, either the entire interval works or the entire interval doesn't work. So if I draw my V so that it crosses every time where I have a solution, which means never, then I go back to the original problem and say, when is the V above the horizontal line? Well, that would be always. The V is always above. So we do get the same answer of always, meaning negative infinity to infinity. Both ways we approach it. Obviously, the common sense approach was much easier, though. We got to the answer a lot quicker. Now, similar is going to happen if we have an absolute value less than a negative, is we, again, have 2 separate approaches. We can take the common sense approach, which is to say, when are positives less than negatives? And the answer there is, of course, never, which means there is no solution here. Our answer is no solution because this can never happen. We can never have a positive that's less than a negative. And if we approach this the same way with our 3-step process, where step 1 is to pretend like this is an equation and you get no solution, step 2 is that you plot no solution, and step 3 is that you figure out where this gets shaded. Well, now we're asking, when is the V below the horizontal line? And again, then, the answer is never. The V is never below the line, and therefore it's no solution. And so we can approach these in either way. I would suggest the common sense approach, that if you see an absolute value on one side, negative on the other, always use the common sense approach, whether it's an equation, whether it's a greater than inequality, or whether it's a less than inequality. Always just replace the absolute value with the word positive, replace the negative number with the word negative, and simply ask yourself the question. Do not go with the knee-jerk reaction of no solution. Because remember, if we look back at this, that wasn't no solution. That was quite the opposite. That was infinitely many solutions. It's all real numbers that worked. for the last example in this lesson, I just want to go over a couple of weird situations that can arise and how we'd write the answers to some of these weird situations. So in this particular one, we have an absolute value is greater than 0. We can go through our normal three-step process here, and we start off by pretending like this is an equation. Absolute value of x plus 2 equals 0. Do we have an absolute value by itself on one side? Yes. Is the other side non-negative? Yes. 0 is not a negative number. Therefore, we can use the absolute value property, which tells us we can set x plus 2 to be equal to 0 or x plus 2 to equal negative 0. Well, negative 0 is just 0, so we just get the answer of negative 2 twice. Now, we're not going to actually identify it twice. We're going to say it's one number. So when we come over here to figure out what gets shaded, we only have negative 2 as our border point. Negative 2 has an open circle because our original inequality didn't have or equal to. So we do not want to include that point. Now, if we want to use the V method again, we absolutely can. We're supposed to draw a V that intersects our line at the solutions where we have drawn. So if I want to draw a V here, the way that we do that is the point of the V is right there. So now instead of the pattern we're used to of above, below, above, if we look at what's happening now, we only have two chunks we're looking at. The chunk on the left, the V is above. The chunk on the right, well, the V is also above. It's not below the line over there, it's above on both sides. So if we go back to the original problem and say, when is the V, well, greater than means above the horizontal line. Well, it's on both sides. It's on the left. It's on the right. Which means we have the interval on the left, which is from negative infinity to negative 2, but not including negative 2, as well as the interval from negative 2 to infinity. Now, in layman's terms, what's happening here is it's everything except negative 2, which should make sense, common sense, if we look back to the original problem and say, when's an absolute value going to be bigger than 0? Well, pretty much always, just as long as it's not equal to 0, because it's always either bigger than or equal to 0. So we have to write it in this way then to say the left chunk is one interval, but I can't continue on without lifting my pencil because negative 2 is not included. So then I have to list the right chunk by saying negative 2 to infinity. So that's one weird situation where there's a 0 on the other side. Here's another situation that's kind of weird as well, just in how we're going to write our answers, because so far all of our answers have had an infinite number of answers, and so we've listed it as an interval. Now on this one, step 1 is pretend like this is an equation. Do we have an absolute value by itself on one side? Yes. Is the other side non-negative? Yes. So we can use the absolute value property and break this up into two separate equations. And like before, we're going to get negative 2 for both. And so we only list it once. Looking back to the original inequality, though, this one has a closed circle because we were allowing equality. Now, like the last one, we would draw the V by just making the point of it hit there since we only had one solution. Like the last one, we only have two chunks, the chunk on the left and the chunk on the right. The V is above the line on the left, and the V is above the line on the right. So then we go back to the original problem and say, hey, what did we want? We wanted the V to be below the horizontal line. Where is it below? Never. So we're not going to shade the left and we're not going to shade the right. So looking at the number line then, what is our answer? Well, we have a dot at -2. That dot means x equals -2 is the only answer. We don't have an infinite number of answers. We only have one answer. So if we wanted to use symbols, we could use the brackets, or the braces rather. The braces with -2 is one way, or we could just simply write x equals -2. But we have a single number answer here. In common sense, if we go back to common sense here, we want to know when an absolute value is either going to be less than 0 or equal to 0. It's never going to be less than 0, but maybe it could be equal. And that's the point that we're allowing. We're allowing the point that where the absolute value is equal to 0, which happens at x equals -2 in this example.